Hi everyone and welcome to this video. So last time we introduced the concept of upfield networks and we have shown a few examples and we have shown an implementation in Turbo Basic how to implement an upfield network on the Atari. Previously, before this video, we also introduced another concept that is coming from neural networks, which is the feed-forward neural network. So in this video, we are going to continue to describe new kinds of neural networks, and in this particular video here, we are going to introduce autoencoders, the main concept and what they are used for. We are going to spend a few words on how to train autoencoders. I'm not going to train an autoencoder in this video, but I'm going to show you how this can be done. Eventually, we will take for granted that we have a pre-computed autoencoder and we will implement it on the Atari Basic. Eventually, we will run a few examples so that it becomes very clear how one can implement and use an autoencoder in Atari Basic. As usual, I am reporting a few links here. The first two refer to the material that you need in order to follow the examples that I'm going to show in this video. So you will need, first of all, an emulator for the Atari, so you can find it in the first link. And you will need also Turbo Basic or Basic if you can find Turbo Basic. And you can use the second link to actually find a few guidelines on how to find Turbo Basic. Eventually, I'm also sharing these two links here because these two links provide a software package, or two software packages actually, to train an autoencoder. So I'm going to spend a few words there so that you can know how to use those. As usual, I am also sharing some material, some scientific material, so that if you are interested in knowing more about autoencoder, you can. I would strongly suggest you to start from this Wikipedia article because this is very simple to follow, and once you can understand an autoencoder, this article is full of references that you can use to dig deeper into this topic. As usual, I want to thank all of you for continuing to subscribing, for leaving comments, for sharing the videos that I am posting online. So thank you so much for doing this. This is very encouraging. This compels me to create even more videos like that. Let's introduce now the concept of an autoencoder. So as you can see in the figure here, an autoencoder is still a neural network. As you can see, you have neurons, artificial neurons, that are represented by these colored circles. And you have connections between the neurons, which are represented by these black lines that you see on the screen. And in practice, the left-hand side layer is essentially your input layer, and the right-hand side layer is the output layer. But this is not just a neural network, of course. This is a very specific, very particular neural network that has a very specific architecture. And the architecture that you see here, it's of course a simple one, but it has all the main characteristics of an autoencoder. So first of all, the first thing that you have to have in order to have an autoencoder is that the dimensionality of the input layer and of the output layer has to be the same. So it means that if you have 5 input neurons, you need to have 5 output neurons. Then you also need to have this particular structure that you see here, where essentially you have a few layers that are hidden layers, which are represented by the green circle that you see here, the green neurons, and eventually you need to have between the two hidden layers, or let's say between the two sets of hidden layers, you need to have another layer which is called the latent space or the latent layer. What does all of this means? What are we trying to achieve with autoencoders? As you can see here, what we are trying to do, first of all, it's a reduction of the dimensions of the information that we are treating. In other words, what you would like to obtain with an autoencoder is that the input and the output remains exactly the same. So this is an unsupervised learning problem. And you would like to have on the red layer here, on the layer where we have the red neurons, which is the latent space, we would like to have a dimension that is smaller than the dimension that we use for input and output signals. Why this has to be smaller? Because in practice we want to have a space, this latent space, which provides only meaningful features representing the data. So in practice, if your data, for example, is an image, let's say an image of a dog, your latent space there should become something that is smaller than the dimension of the images of a dog that you are providing. So if the dimension of the image you are providing is practically represented by the number of pixels that you are treating, you would like to have your latent space with much less, let's say, with a much smaller dimension with respect to the dimension of the input data. So in practice, what we are trying to achieve here is that essentially we would like to have in the latent space, we would like to find the right feature that represent the signal that, or let's say the input that you're providing to the network. So if, for example, you are presenting pictures of dog, you would like that the features there are representing something that is more characteristic of a dog. So maybe a neuron is representing let's say the face of the dog, or another neuron is representing the nose of the dog, or the length of the ears of the dog, and so on and so on. And why do we want all of this? For that I need to show a different picture here, which is this picture that you see now. So in practice, at the end, if you can come up with an autoencoder that is trained properly so that the input is precisely what you get in output, and the latent space has essentially dimensions that are smaller than the input dimensions, in practice what you get here now is that you can split the network in two, and you obtain an encoder and a decoder. And the decoder becomes the part that is very interesting, because in practice now you can use the latent space. So you have now a space of latent variables which represent features of the signal that you are treating, and you can generate new pictures of a dog in this specific example that I have reported, that are essentially represented by variables in the latent space. So this is a way, for example, to achieve generative AI that everybody's talking about. You practically train an autoencoder and then you split it into an encoder and a decoder, and you use the decoder for the generative AI part. These kind of networks can be used also for very engineering related tasks. For example, you can also think of having a bunch of let's say signals that are coming from a sensor, or let's say a bunch of signals that are coming from a bunch of sensors, and you want to make sense of these signals. You might for example suspect that you have too many signals and they are actually representing something that is simpler, and you would like to find the simplest model that still represents the signal. So one way to do this would be to use an autoencoder. You would train it the way we are going to see, and in practice you will then split the autoencoder in two so that you have a decoder. So from the decoder you would be able to play with the latent space, and essentially the latent space would represent the simplified model that you are looking for, this particular signal that you are receiving from the sensors. So now we are going to spend a few words on how to actually train those autoencoders. You will see that I'm just going to go through the tenets, but you should be able to use these tenets to actually train a network like that. How are autoencoders trained? The figure that you see here, it's practically an extract from the Wikipedia article that I was just talking about at the beginning of this video. And I'm reporting this extract because it practically explains what I have just explained about autoencoders being made of a decoded part and an encoding part. But it does that in a more mathematical fashion. So this is going to be easier when we talk about the actual training of such a network. So what the article says here is that an autoencoder is defined by the following two components, and the two components are essentially two sets. This is the first component, and the second one is two parameterized families of functions. So what do we mean by two sets? So first of all, we will have a set or a space of decoded messages that we are going to call X, and the set or the space of encoded messages that we are going to call Z. And typically X and Z are Euclidean spaces, and they have a dimensionality. But in a way, what we want to achieve is that the dimensionality of X is always bigger than the dimensionality of Z. So in practice here, X now represents the space of input that you are presenting to the neural network, and Z represent the latent space that you are looking for. And of course you would like to have the latent space with the dimensions that are smaller than the input space. Then now if we move on the second component that define an autoencoder, we have practically two parameterized families of functions. The first function is going to be the encoder family, which is now defined as E phi that goes from X to Z, and it's parameterized over phi. So practically this phi here, you can think of this as a set of parameters, in this case weights and biases, which are defining the encoding part of the autoencoder. And then we also have the second family of functions, which is the decoder family that we call in this case D with theta, that goes from Z to X. So the parameter now is theta, where theta is again an ensemble of parameters that we are looking for, and this is represented in this specific case by weights and biases. So in this particular case, the decoder of course goes from the space of, or let's say the latent space, to the space of inputs, which coincides with the space of output signals that you can get from the network. So at the very end, how do you train autoencoder? You have to practically define a loss function, which is the function that you see here at the bottom, and which is defined by L of theta and phi. And what you are going to do is you are looking for the parameters theta and phi so that it minimizes the loss function. If you have a careful look at the loss function, you will see that this is essentially the distance between the input that you are providing to the autoencoder and the output that you get from the autoencoder. And essentially what you would like to have is that this is minimized so that the output that is provided by the autoencoder is very, very similar or very, very close to the input that you are providing to the same network. So essentially that's what you are going to do if you want to train an autoencoder. And in one of the next videos, I'm going to show you how you can actually do this, how you can achieve a training in BASIC on the Atari. But for now, I would say you can still rely on the libraries that I have mentioned at the beginning, which are FANN or neural networks, because you would be able to train your neural networks and then you would be able to obtain the set of weights and biases that you need to migrate over the Atari so that you can run the autoencoder in BASIC. before we can implement the autoencoder, or before I can show you how I have implemented this autoencoder in BASIC, we need to focus a little bit on this picture that I am showing here on the screen. And we need to focus on this because I have reported here a few labels that are going to be very useful once we run the autoencoder on the Atari. So first of all, here you see that we have a set of input neurons which are practically in the input layer, and these are going to be 5 neurons that we have here that you see on the left hand side. On the right hand side we will have our output layer that is represented again by the same number of neurons, which is again 5, but these are now output neurons. And we will have only 2 hidden layers, one for the encoder, one for the decoder. We are going to call them H in this particular case. These are the ones that you see in green. And we will have one hidden layer for the encoder and one hidden layer for the decoder. Each hidden layer will be made of 3 hidden neurons. And finally, we will have one latent space, which is represented by the layer with these red neurons. And we will have only 2 neurons in the latent space. So we can now move on and see the implementation of the autoencoder. So the very first thing we are going to do is to list the program so that you can stop through the listing and have a careful look about what is it that we are implementing here. And now I'm just going to explain every single part of this program so that it becomes easy to understand what has been implemented. The very first thing we are going to do is to show lines from 10 to 29, where essentially we have a few declarations and a few initializations. So on line 12, as you can see, we are defining the input of the autoencoder. Since we have 5 neurons, we are going to have an input that has 5 values, or let's say 5 components with different numbers. In this particular case, on line 12, what we are doing is we are simply providing random numbers ranging between 0 and 1. Then on line 15, what you see here is that we are defining the total number of neurons, but we exclude the input layer because the input layer is not going to provide anything in terms of neurons, it's just providing the input. So line 15 becomes the number of neurons, which is 3 plus 2 plus 3 plus 5. 5 is the number of output neurons that you have. 3 is the number of hidden neurons that you have for each hidden layer, so in this case 2, and 2 here is the number of neurons that you have in the latent space. On line 18 we are doing something similar, but this time we are computing the total number of weights. If you go through this simple formula here, you will understand very quickly how the total number of weights was calculated. If you have a look at the picture that I have shown previously, this will become very, very simple, almost trivial. On line 20 then, we start to allocate in memory a few arrays that we need, and in particular on line 22 we define the arrays W, which are going to contain the weights. We define the array B, which is going to contain the biases of the neurons, and eventually we are going to define the array O, which will contain the output for every neuron that we have in the autoencoder. Then starting from line 25 until line 29, what we do here is that we assign an initial value for the weights and the biases. In this particular case, for now, we keep everything equal to 0 because we are going to run a few examples to see what happens. So now we can go ahead and show just line 30, where on line 30 essentially we have a remark which says that we start the inference. So we are now going to dig into the inference, how it is made in an autoencoder. So we can now go through from line 32 to line 60 and see what happens. So in these lines here, this part of the program is essentially implementing the first layer, or let's say the first hidden layer of the autoencoder or of the neural network. So since we have 3 neurons in the hidden layer, we will have a main for loop here that starts at line 35 and ends at line 60 that will go from 1 to 3. And then essentially on line 45 and on line 50 we compute the discriminant of that particular neuron. At the end, at line 55, we compute the output of the neuron. In this particular case, as you can see, we are using a very simple activation function, which is the sine function. So we can now proceed further, and we are going to analyze lines from 65 to 90. And what you can see here is that essentially we are implementing now the latent layer, which corresponds to the second layer if you consider the autoencoder and you remove the input layer. So in this particular case here, we still have a main loop which goes from 1 to 2 and starts on line 70 and ends on line 90. We have only 2 cycles in this loop because we have only 2 neurons in the latent space. So what we do on line 75 and line 80 is the usual. We are computing the discriminant for every neuron that we have in the latent space. And on line 85, eventually we compute the output of the neurons in the latent space. Again, you see that I am using a very simple activation function, which is the sine function. So I'm keeping things very simple so that it's easy to follow the implementation. So we can now proceed further with the listing, and we are going to go from line 95 till line 120, where we now find the part that implements the third layer, which is the hidden layer. And in this particular case, this is the second hidden layer that we have in the autoencoder when we go from left to right. So on line 100, we have a for loop that goes from 1 to 3 and close at line 120. It goes from 1 to 3 because we have 3 neurons in the second hidden layer. And on line 105 and 110, what we do is the usual computation of the discriminant. On line 115, we compute the output of the neurons that we have in the second hidden layer. Finally, we can go on the rest of the program here that goes from 125 till 150, and this is the last part of the program that deals with the autoencoder inference. So in this particular case, now you get it. This is the output layer, so the final layer of the autoencoder, and we have a for loop that goes from 1 to 5 because we have 5 neurons in the output layer, and on lines 135, 140 we are computing the discriminant of those neurons, and finally on line 145 we compute the output of every neuron that we have in the output layer. So the final part of the code ranges from line 160 to line 190. This is a very simple part to understand. We practically print the results. So the first part shows the input, and the last part of this code here is going to show the output that one gets from the neural network. So if we now run this code, you are going to see something that is expected. Since we have set every weight and every bias equal to 0, if we run it, you see what is going to happen. No matter what the input is, the output is always 0. And this is expected because since every weight and every bias is 0, we don't expect to see anything different than getting 0 in the activation function, and therefore in the output of every neuron. So we can change this a little bit, and to change this we are going to change the initial part of the code where we are setting the values for the weights and the biases. So if we start by changing only the biases, so I'm just going to add here some random numbers just to see what happens. This is what we get. So I've just changed line 29 so that now the biases becomes random numbers between 0 and 1. So if we run now this autoencoder, you will see that things now changes because now the biases are not 0 anymore. So this means that in practice we now start to have an output from the autoencoder which is not trivial. But as you can see, this output is also very different from the input, and that is because we are just using random numbers for the biases, so the network has not been pre-computed. So if we now try to change something else, like line 27, where we define the biases, the weights, you can see that things becomes even more interesting. So we are going to define this as a random number again that ranges between 0 and 1. And now if we run this code, you will see that the output that we get is even less trivial than the previous one. So if we now run this, you see that we get something that is not very easy to predict. And as you can see, the values that we get there are very different from the input. Again, this is because we haven't trained the autoencoder. This finalizes this video for today. As always, I want to thank you for being here and for your attention, and I hope to see you in the next video.